All right, back from break. I guess we wrap up chapter 37 here. So we were just before break. We had gotten to looking at some examples. Let me go back and look at these. We had looked at examples of particles, electrons, protons, neutrons, whatever. And using these formulas, these are general equations from quantum mechanics. So I'm going to claim that's the fundamental starting point for quantum mechanics. Those formulas are the starting point for determining all of the interference effects that take place in quantum mechanics. And we did this problem, we just did this before the break. But we were able to go in and get a frequency for these electrons and a wavelength of the electrons based on their energy and momentum. That's going to be something you're going to want to do. Take a look at the homework problems. Definitely problems like this will be on the midterm also. All right, and then we had talked briefly about using electrons, and so this kind of takes us into the next problem here. We can use a beam of of photons of light. You guys may remember X-ray crystallography or X-ray diffraction. You could send X-rays through crystals to help determine the crystal structure. So in a material, there is often a repeated pattern of nuclei, a lattice, a crystal lattice. And what that means is that the molecules, if we take molecules of a material and create a crystal structure where they're all aligned in a repeating pattern, that becomes a diffraction grating. So if you remember, diffraction gratings are when we had made slits or etched lines in a material that were very evenly spaced. Well, naturally occurring materials are just diffraction gratings if they have a crystal structure. So if you look at the picture here, this is drawn as maybe the simplest crystal structure is cubic. Something like a crystal of salt, sodium chloride, has a cubic crystal structure. Now, crystal structures get much more complicated, but over the years, over the past 100 years or so, researchers have developed better and better techniques of interpreting the diffraction patterns that come out. So you guys may be aware that the structure of DNA, this double helix structure, was first figured out. Rosalind Franklin, a prominent physicist who developed many of these techniques, was able to interpret what was going on in the DNA molecule from crystal structures of DNA. So anyway, in this example they have here, we've got a beam of electrons coming in. Now they're scattering off those front row of the atoms, and it tells us in this very long problem. We're using the electrons from the previous example, which have 100 eV of kinetic energy, and we see a diffraction grating maximum at 24. So I got a little confused here too, because if you remember from chapter 35, diffraction grating is a terrible name for diffraction gratings because it's not diffraction, it's multiple slit interference. So that's what this is. It's multiple source interference. Let's see what the picture looks like here. So I have a crystal structure here, and I've got a regular array of repeating pattern of nuclei and electrons. So we're sending electrons in, they're scattering, and since there's a regular array, there's many paths. So the electron coming in doesn't just interact with one nucleus. It can interact with many of these nuclei, same thing that the photons did, right? They went through all the slits. And so the paths that the electron could follow in returning could reinforce each other if there's a path length difference that puts the two paths, or the 3 or the 4 or 5 paths, into constructive interference alignment. And so we're going to use our formula for a diffraction grating for multiple slit interference. And we can solve, what they want us to solve for here is the spacing between the atoms. Well, we can do that. We know that it's first order. We know that the first order peak shows up at 24 degrees. All we have to do is come up with the wavelength of the electrons that we're using. So we can control that. If you think about this, an electron, we can control the kinetic energy. We just set up a certain voltage, and that voltage will control how much kinetic energy the electrons pick up. So that's the idea. Again, we're going to go back and do the same calculations as before in terms of kinetic energy, but this time I'm after momentum. In order to get the wavelength of an electron, I need to get the momentum figured out. Now, with photons, the energy and the momentum were the very same number, but with electrons, they're not. So I really need to go after the momentum. So I did this. I went back to Physics 4a and said, you know, sometimes in Physics 4a, we would write the kinetic energy as p squared over 2m. So the kinetic energy, instead of using velocity, we could write the kinetic energy in terms of momentum. Now, I put a couple of extra factors of c in here and solved for pc, and I got this formula right here that needs a square root sign that got dropped. That needs to get a square root sign on it. And so I solved for pc, and the momentum value we got is 10,110 eV. That's the same thing we got before when we did this problem. So 10,110 eV, I plug that in, I put in my 1240, the wavelength is 123 picometers. So this is the wavelength of the electrons, and I can plug that into my interference formula from multiple slit interference, and it says that the spacing within the crystal is about 300 picometers, 301 picometers. Okay, that seems okay. Atoms and spacing within atoms is typically a few hundred picometers. This might be a little bit on the long side, but that's certainly within the range of chemical bond lengths. So there's an example of interference using electrons. And again, we can build electron microscopes and control their voltages, and using magnetic fields or electric fields, we can speed up the electrons, we can focus them. Electrons are charged, so we have much better control over the energy of the electron beam and how tightly focused the electron beam can be for an electron microscope. All right, I guess the rest of the chapter, we'll see how this goes. I think we're on schedule here. I think we'll wrap everything up in time here in today's lecture. But we're going to do just a brief bit of history, but then we're going to start looking at some different models for atoms. So let's take a look. Early models of the atom, around what do we want to say this was, 1915? Or 1900 actually. What happened was electrons were discovered. It was discovered that almost any material, if you put it in a vacuum tube and you put a high voltage source on it, you could generate a current. Any material, you could drive these electrons off and you could measure their properties. And it was found that the electrons were really light. The masses were really, really light, much lower than the masses of atoms that had been measured. So it seemed like the electrons were not much of the mass, which is true. The electrons do not make up very much of the mass of atoms and molecules. So initially, at least, there was this plum pudding model, which I think we just continue to introduce that because it's fun to say plum pudding. But there was this plum pudding model of there was positively charged stuff and the electrons were somehow embedded within this positive stuff. All right. Now, in around 1915, maybe they give a year here, they didn't. I think it was 1915, Ernest Rutherford ran some experiments. Radioactivity had been discovered, and they could take what were called alpha particles, they're helium nuclei, coming off of radioactive materials, and direct them towards a thin sheet of metal. I think it was gold. Gold really has nice property. You can make thin, really, really thin sheets of gold. And what Rutherford found was that the alpha particles, for the most part, went right through. So the alpha particles were able to go through the gold, but occasionally the alpha particles would hit something. Okay, so the alpha particle occasionally would end up coming straight back. Now, what that meant was the alpha particle, which was known to be much, much heavier than the electrons, must have run into something that was even heavier. To have the helium nuclei, the alpha particles, actually be sent back with almost the energy they came in with, that would require something with much, much more mass, and it would need to be concentrated into a smaller object. So Rutherford and other physicists started thinking in terms of, well, this is a little crazy. It seems like within materials, there's a nucleus that contains, 99.9% of the mass. So this was the first recognition of the atomic nucleus, that most of the mass is concentrated into a really small area. And if we fire objects through, as in this case, these alpha particles going through the material, the electrons were not heavy enough. It's colliding with electrons, but the electrons are so low in mass compared with these alpha particles. The alpha particles were able to make their way through because the nuclei take up very little space. It's very unlikely that you would run into a nucleus. If you make these gold sheets thin enough, you're not going to hit one of the gold nuclei. And running into the electrons is not going to cause an alpha particle to reflect back. It's not enough concentration of mass. So estimates were that this nucleus was in the size of femtometers, 10 to the minus 15 meters. All right, so that's kind of the discovery. Now, along the way, what people also found out about different materials is that you could make them glow. And when you would put different materials, now it says a very thin gas here, so you could easily put helium or hydrogen or argon into these tubes. You could also put you could put mercury in, and you would get a little bit of mercury vapor generated, for example. So anything that would have a little bit of a vapor pressure to it, you could put into a high voltage tube, and you could get them to glow. Now, what's happening here is you're accelerating electrons, and you're mapping out the different quantum states for the electrons in these different materials. But these atomic spectra became very important in analyzing atomic structure. Now, the simplest sort of atom, hydrogen, had a very regular pattern. There is this constant called the Rydberg constant. It has this value to it. We'll see, we can actually derive this and find out where it comes from. But researchers, just playing around with the numbers, found out that the wavelengths of light being produced in hydrogen could be calculated using this Rydberg constant and writing 1 over the wavelength as a Rydberg constant times 1 over an integer squared minus 1 over another integer squared. And it matched up really well. So here is what it looked like. This is looking at hydrogen and seeing if I shine light through, if I heat up this hydrogen, what lines are produced within that hydrogen gas. Now, there are photons within the visible spectrum, but there are also photons within the UV and the infrared, which researchers began to be able to measure using different types of instrumentation. So you could look for all of these different energy photons, and it was found out that there was quite an extensive number of lines, but it was found that they all fit this one formula. Everything going on in these hydrogen atoms fit this one pattern. Now, Niels Bohr worked from this spectrum information and started thinking in terms of quantum states, particular energy states of the electron within the hydrogen atom, and started playing around with different formulas to see if he could derive something that would explain these experimental formulas, these formulas based on observation. And Bohr was successful in doing that. Now, along the way, Bohr made some incorrect assumptions. So I think we already talked about this a bit, possibly. But Bohr, Niels Bohr, Danish physicist, was able to develop a formula that correctly predicted all of the quantum states of electrons inside hydrogen by making a series of wrong assumptions. And I always, I say that's a great skill to have, starting with a series of wrong assumptions and getting the right formula. But where Bohr was absolutely correct was the existence of different quantum states, different energy states of the electron. Now, the diagram here says, let's imagine there's an electron, it's in some energy state, but it loses energy and drops into a different energy state. The difference in energy, if energy is conserved, that difference in energy could generate a photon. That could be how light is generated in atoms and molecules. Now, we could reverse that process. We could have a photon of light come in and take an electron, it could be absorbed by the electron, and that would boost the electron back into the higher electron state. So it's this energy conservation reaction taking place between electrons and photons once again. That's been very common in chapter 37. Now I put a yellow box around this little squiggle again. Notice that for the electrons, they call the energy E, but for photons, they call it HF. Why don't they just call it E? And why don't they just use a straight line for the photons? So that's what you're going to see in my diagrams. But this was really an important step in developing quantum theory. Now, Bohr, it says here, found that the angular momentum is quantized. It turns out his angular momentum quantization formula is wrong. So, now, the way Bohr derived this is that here's a nucleus. The nucleus has some number of protons in general. We're not exclusively hydrogen yet. So we could imagine any element, and depending which element in the periodic table you pick, it's going to have some number of proton charges. So each proton has a charge of E, and Z is what's known as the atomic number. It tells us which element it is, and you guys know from the periodic table, the elements are arranged according to how many protons they have. So every possibility, every possible element is listed in the periodic table because there are no gaps. We know specifically this number of protons says it's this element. This number, if it's 6 protons, it's carbon. If it's 12 protons, it's, what is 12? Phosphorus, 10, 11, magnesium, right? Anyway, so now Bohr, playing around with formulas from classical physics, imagined, what if you had an electron in a circular orbit? Well, that's just ridiculous. if an electron was in a circular orbit, the atom would be flat, right? It wouldn't be three-dimensional. Anyway, this is the way the Bohr model comes about. So Bohr had taken physics 4b and physics 4a, and Bohr knew about the electromagnetic force, in particular the electric force. So here is the electric force. Let's just do the whole thing here. So the first thing we want to point out is it's not correct. My grandmother was Danish too, but still the Bohr model it's not correct. The Bohr model for hydrogen said here is an electron going around in a circular orbit. There's a force attracting it towards the proton nucleus. The acceleration is in that direction. So we're imagining here circular motion, which that's not what's going on. That's completely wrong. So the Bohr model is based on all these incorrect assumptions, but at the same time, it gives us a chance to go back and review physics 4a and physics 4b a little bit. So here we go. Here is a force acting between two charges. It says the force between the proton and the electron is given by little k e squared over r squared. Now, I didn't write down. Little k here is the electric force constant. Go back to chapter 21, where our textbook first introduces that formula, and the value for k is 8.99 10 to the 9th newtons meters squared per coulomb squared. Now I know the textbook introduces it that way, and then they stop using little k, but they use 1 over 4 pi epsilon naught instead. Now I'm going to go back and use little k because it's simpler. And so there it is. But again, the textbook does introduce that at one point. Now the acceleration is given by F over m, so the acceleration of that electron, k e squared over m r squared. And then circular motion says a is to v is to r. That gives us this formula right here. It says that for a circular orbit based on electric forces, we would have mv squared equal to ke squared over r. And that's the relationship we want to use, because what we're interested in is finding out how much energy the electron has. And ke squared over r and mv squared, they sound like they're kind of related to some energies. First of all, the kinetic energy of the electron would be 1/2 mv squared, so that's like twice the kinetic energy. Meanwhile, the potential energy between the electron and the proton would be given by ke squared over r minus. It's an attractive force. So that's what the energy of the electron looks like. Now we can take this relationship and replace mv squared with ke squared over r and find out that I can write the total energy, including kinetic and potential, as minus 1/2 ke squared over r. Now the minus sign is important. If you remember from physics 4a, if the overall energy is negative, that says that the orbit is stable. It says that it's a bound state. And hydrogen is a stable state of a proton and an electron. If the overall energy went positive, the electron and proton would fly apart. That would say there's enough kinetic energy that the potential energy is not holding it together. So anyway, that's the energy in a circular orbit. Now here is the angular momentum quantization that the slide mentioned here. Right there, angular momentum is quantized. What Bohr tried different things, I'm sure. Bohr said, what if angular momentum is some multiple of Planck's constant? Now, this is an alternate version of Planck's constant. It turns out that not only do we use Planck's constant in a lot of formulas, we use what is considered to be an angular version, a radians version of Planck's constant, and that is h over 2 pi. So instead of cycles, we're thinking of this in terms of radians, and we designate that by crossing our H's. So by the time you complete Physics 4C, you'll be crossing all your H's. It'll be great. In your English class, make sure you cross all your H's. When the instructor asks about that, say that's Planck's constant. It's a factor of 2 pi. Now, if you guys remember angular momentum from Physics 4A, that's pretty good. Most students, with a little nudge, are going to remember. If you remember, an object with mass m, which is that electron, moving at speed v at a distance, a circular orbit of r, that's angular momentum. Orbital angular momentum is mvr. And so we're going to take that and set it equal to some multiple of Planck's constant. Now you might be saying, why would anybody do this? And it's because we're desperate, right? Scientists get desperate and they go, what could be the underlying principle? Maybe it's angular momentum. Now, if you think back to Physics 4A, what were some of the major players in thinking about what important physical quantities were there? Well, energy was conserved and linear momentum was conserved. Well, angular momentum was conserved too. So that seemed like something natural to try out, and Bohr did. So Bohr said, what if angular momentum is quantized? Well, it turns out, fun fact, that the angular momentum is quantized, but that's not the formula. It's more complicated. We'll see this in we'll see this all in chapter 39. So in chapter 39, we're going to come back and we're going to do atomic physics the right way. Full-blown quantum mechanics right from the start, not this Bohr model kind of stuff. So don't let this get stuck in your head. What happens with a lot of students in physics and chemistry and whatever is they kind of get stuck with this Bohr model. Well, the Bohr model is wrong, so we got to move on from that. But the Bohr model gives us the right formulas, and it allows us to kind of view the evolution of thought in science. So that's why we're looking at it. So taking this angular momentum and quantizing it and then squaring it enables us to go in and write an expression for how r is quantized, and we end up with this quantization right here. It says that only certain radius orbits are possible. Now, the electron is not in a circular orbit, but the value of r does give us an idea of how far, on average, an electron is from the nucleus. The electron wave patterns surrounding the nucleus are going to have a certain radius or a certain distance to them, and Bohr's model does correctly predict the size of hydrogen. So Bohr's model predicts that hydrogen in quantum state number 1, and there's a state 2 and a state 3, is at 53 picometers. That's about the size of hydrogen. So that worked, roughly, as just an estimate. Now, what it does predict is when you go into these higher energy states, energy state 2 is 4 times bigger, and energy state 3 is 9 times bigger, and I didn't draw these to scale. But once we get the R value plugged in, we can solve for the energy. If only certain radiuses are possible, and the energy depends directly on radius, then only certain energies are possible. And the formula is this: the energy of the different quantum states, mke squared, Again, the K here is the electric magnetic force constant from Physics 4B. It is not Boltzmann's constant. It is not a spring constant. It's not thermal conductivity. How many things have we used little k for? Maybe that wasn't such a good idea. This is the electric magnetic force constant. This is Planck's constant divided by 2. When we plug numbers in, it says that that's the pattern of energy states. So that's pretty impressive that Bohr was able to kind of predict the size of a hydrogen atom. Now, using this energy formula, this one right here, right there, the energy of the possible quantum states, where n is equal to 1 or 2 or 3, some integer number, if we start from those energies, Bohr was able to calculate, here are the energies lined up. So this is the Bohr model. If you look down here, here is energy state number 1, and it's at minus 13.6 eV. And that's telling us how much binding energy there is in a hydrogen atom. Binding energy between the electron and the proton. The next available quantum state, quantum state number 2, has a binding energy of 3.4, quantum state 3, 1.5, 0.8. So what's happening here, according to that formula, is that the quantum states are getting closer and closer to energy zero. Now, we mentioned energy zero. Energy zero is called ionization. That means that once the energy reaches zero, it's on the threshold of the electron and proton coming apart. So there is no more binding energy when the numbers are no longer negative. So all of these quantum states, these many quantum states exist, but once you have too much energy, the hydrogen atom ionizes, it comes apart. What we could do then is say, okay, all of those possible photon energies would come from all the possible transitions. Those high energy Lyman series, which produced photons in the ultraviolet, those are all electrons dropping into the lowest state, what's called the ground state, number 1. Because look, between state number 2 and state number 1, that's a difference of 10.2 eV. That's already enough energy that you're in the ultraviolet. The photons generated from an electron dropping from state 2 to state 1, that's going to be in the ultraviolet. Well, from state 3 to state 1, that's going to be ultraviolet. From 4 to 1, 5 to 1, 6 to 1, 7 to 1, anything else dropping into state 1 is going to be somewhere between 10.2 and 13.6 eV, fairly narrow range of energies. Those are all going to be in the ultraviolet. Now, when we get to what's called the Balmer series, these are the ones that show up in the visible light spectrum. At least 4 of them do. And those are 3 to 2, 4 to 2, 5 to 2, 6 to 2, have energies that create photons in the visible part of the spectrum. The Passion series, those are dropping into 3. Those are all too low of energy. So the most energy I can get from a transition into state number 3 is 1.5 eV, and visible light doesn't start until 1.77. So any possibility, these are all going to be too much energy. Those are going to be too little energy to create visible light. Only the first 4 of the Balmer series fall within the visible range of light. So here's an example here. Here are states 1, 2, 3, 4. Those are the energies. Here is a table outlining these. And we calculate the energy of the photon. Again, it's an energy conservation equation. Energy of the photon is equal to the initial state of the electron minus the energy of the final state of the electron. So it's these n values that are going to determine how much energy we're looking at. Now, the Rydberg constant, if you remember that formula, it's worth going back, I guess, and taking a quick look. Ooh, here are all these observed wavelengths of light. This formula right here, the one the experimentalists had mapped out, that formula can be derived using the Bohr model. So, by making a series of incorrect assumptions and being wrong about how the atom works, Bohr was still able to come up with the correct formula for the energies. We're going to find in chapter 39, a few weeks from now, after the midterm, when we come back and do chapter 39, we're going to do it right. We're going to do it using quantum physics right from the start, but we're going to get the very same energy formula. That's just crazy that that happens. So do not get attached to the Bohr model. get attached to the energy formula and practice using that, but no circular orbits. So here's a problem. I wanted to come back and look at the Rydberg constant. So the Rydberg constant actually turns out to be this 13.6 EV number, which is right there. That's where the 13.60 EV is coming from, that formula, divided by HC. Now when we do that, what we get for the Rydberg is 1 over 91.1 nanometers. So the Rydberg constant that they introduced us to actually is an inverse wavelength. And it's 91.9, and the Bohr model exactly predicts that number. Experimentalists had determined that from experiment, but the Bohr model predicts it from theory. Incorrect assumptions, by the way. So here's the Bohr model. If we drop from n equals 2 to n equals 1, what's going to be the energy of those photons? Here we go. Here's the general formula. That can be written as, I can take all of this stuff and just calculate it up front. That gives us minus 13.6 EV. Now, in some of these problems, there's always we're always doing subtraction, and so I wrote this out to more significant figures. Now, you can look, these have all been measured very accurately, so that's a pretty good numerical value for that. 13.6057 EV. Oh, here we go. There's the electromagnetic force constant right there. So again, chapter 21, the first time our textbook introduces electric force, the first few examples, that is being used. Now, if you guys took Physics 4B in my class, I continued using that all the way through electric and magnetic forces and fields to provide better unification for those topics. Now, what we can do then is find out how much energy we have in state number 2. That's 3.4 EV, negative 3.4. State number 1, negative 13.6. The difference is 10.2. It's taking a negative and subtracting something that's more negative to get a positive. And then I can take, that's the energy of the photon. That is in the UV part of the spectrum. Using my 1240 conversion, that worked out to be 121 nanometers. Again, the UV part of the spectrum. What about a different transition? So it's the same problem, right? Except that now we're going to go from state 6 to state 2. Same diagram, same calculation. It's just that this time, when I calculate the electron energies, I'm going to be putting in 6 and 2. Now, when I put in 6, I got 0.378 EV. And again, I kind of went overboard with this. As the ground state, the 1/2 m ke squared over h bar squared. So I can keep some extra sig figs here. So I got an energy for those two states. Again, I'm subtracting a lower negative value from a higher negative value to get a positive value. It says these photons would have an energy of 3.02 EV. I can take my 1240 conversion and get to realize that the wavelength is 410. Now, those are visible numbers. 3.02 EV, that's within the range. Visible light goes out all the way to 3.1 EV. Or in wavelengths, it goes all the way out to 400. So it's way off in the violet end of the spectrum, the blue or violet end of the spectrum. But it's there. We can see that in the spectrum of hydrogen. Now here it says, what's the maximum wavelength of hydrogen that the ground state could absorb? So let's say we have an electron already in the lowest state. Saying maximum wavelength, that's confusing. Instead of saying maximum wavelength, what they could say is what's the least amount of energy a photon would need. So let's say it that way. So I've got an electron in state number 1. What is the least amount of energy that a photon could have to create a transition? And that would need to take me to state 2. So let's do that. These are just becoming repetitive, right? So the energy that the photon would need to have, the longest wavelength means minimum energy, and I don't have any available quantum states between state 1 and state 2, and that distance requires 10.20 eV. So that's how much energy. Now, I didn't do the wavelength. They did ask for wavelength. But we can convert that. We can use the 1240 nanometers EV conversion to find out what that wavelength would be. So that's going to be UV. Now, if I don't have a photon with this energy, what's the next lowest I could use? And I could use 12.1. If I go in and calculate the energy of state 3 and subtract off the energy of state 1, that's what I get. Now, I'm using kind of a shortcut version on these, where I've got 1 over the final state, or, yeah, I guess we're adding photon energy here. So it's 1 over the lower state squared minus 1 over the upper state squared. So I've factored out the 13.6. I'm using kind of a shortcut version for these calculations. Go back and check. That's a good way to practice these. We've done these a few times now, and so each time I'm using less and less math, I guess, because we've seen it before. Now, what would happen if instead of hydrogen, we were looking at helium? So the helium ionization energy, now it's saying that we already start, this is a little tricky, it says that we're already starting with helium with 1 electron is missing. How much energy is it going to take to remove the second electron? Now the reason they ask that is because the Bohr model will work as long as there's only 1 electron. And helium plus, helium that's already lost 1 of its electrons, it only has 1 left. And all of the mathematics that went into hydrogen, it works for helium plus. It works for lithium plus plus. It works for beryllium plus plus plus. As long as there's only 1 electron left attached to that nucleus, the Bohr model will work. Now what we do have to do, if we go back to how the derivation worked, the nucleus now, instead of having a charge of E, is going to have a charge of Z times E, where Z is the atomic number. Z is telling us how many protons we have in the nucleus. Now, no matter how many protons are in there, the nucleus is still so tiny, we can treat it as a point charge, but we do have to take into account the increased amount of charge. So the Bohr model works, the energy formula, we just have to add a factor of Z squared. Where we used to have E, it's now going to become ZE squared, and there is a square right there. So I do have to go through, we need to get a square added right there. Okay, anyway, KE squared right there. Now what that's going to do is it's going to boost all of these energies by a factor of 4. So if we use ionization as a reference, what that does is it pulls all the energies down. Each one of those energies is going to drop by a factor of 4 when I switch from hydrogen to helium plus. If I went to lithium plus plus, everything would get pulled down by a factor of 9. So 2 squared is 4, 3 squared is 9. When I do that, the energy required would be 54.42 eV. The wavelength would be, whoa, that's pretty short, 22.8 nanometers. So we're getting down to some pretty short wavelengths, and that continues through the periodic table. All right, now I think we're coming up pretty close here to the end of the chapter. I think we're gonna. This is gonna work just about right. I don't think we're gonna have to go over unless I keep talking about it. So let's go ahead and look at this next example. we have hydrogen at 20 Celsius. Come on, they don't really mean 20 Celsius. They mean 293 kelvins, right? So they're estimating what's the average kinetic energy of a hydrogen atom at room temperature. Well, let's just do this. So, hey, wait, this isn't fair. This is like a physics 4B problem thrown in. So if you guys remember, the average translational kinetic energy of, we're looking at just a hydrogen atom. So it's not a molecule, it's not H2. So I have a bunch of hydrogen atoms, and the translational kinetic energy on average is 3/2 kT. Now this is Boltzmann's constant. So this time it is Boltzmann's constant, and I scaled that down so I could use EV. So I first did this in joules per Kelvin, and I got 6.065 10 to the minus 21 joules. And then I converted to EV. So when I converted to EV, this became 0.0379 EV. Now, just as a reference here, I calculated KT, not 3/2 KT, but just KT itself, in terms of the temperature and Boltzmann's constant. And it turns out that KT, that needs to be in EV, so that joules needs to be in EV. So 0.0253 EV. All right, so this is the average energy of translation for a hydrogen atom. Now, how much energy did we need to boost into the second state? We needed 10.2 EV. And what they're saying is, are you expecting, through just random collisions, that the electrons will end up in excited states in hydrogen? And the answer is no. Typical energies of collision between these hydrogen atoms are a fraction of an EV. It would take 10 EV to jump into state number 2. So it's not going to happen. Now, there's some stuff I wrote in here on the side. There's a field of physics called statistical mechanics, which predicts, if I have a sample of atoms, how many are in the different quantum states, and we can use ratios here, and it's proportional roughly to e to the minus energy over kT, again, Boltzmann's constant. So I calculated this, and at a temperature of 293 kelvins, the number of electrons in the excited state would be 1 electron out of e to the 403. And when I put e to the 403 on my calculator, it blew up. Okay, I should have converted it. Maybe I'll go back in the notes and write this in base 10. But it's 1 chance out of an unimaginably huge number that any of these electrons would end up in state number 2 at a temperature of 293 kelvins. Just from thermal transfer of energy through collisions, that's not going to happen, right? We're not going to find any of those hydrogen atoms in an excited state. All right, the Bohr model was an important intermediate step. It started getting people thinking in terms of quantum states, but it's all wrong, so forget about it. We're going to bring it back in chapter 39. But wait, on the midterm and for the homework, you're going to want to know the energy formula. I think the energy formulas will be enough. Bohr did get the correct energy formula, and we can use that already to say a lot of things about simple atomic systems, how much energy we're looking at. Finally, there's this last topic that's kind of thrown in here, and it's talking about Louis de Broglie imagined that these circular orbits, the reason these circular orbits from Bohr worked is because they represented integer values of angular momentum. And so this started people thinking of interference effects based on angular momentum. And this was kind of the first step towards full-blown wave functions, which I keep advertising chapter 39. That's where we're going to come back and do atoms the right way. So this was another, don't worry about this part of the chapter, okay? But you do have to know the Bohr formulas. So the formulas that Bohr was able to come up with, right, well, all these examples. The Bohr model here, the Bohr model here, all these different transitions. You want to be able to work in terms of, let me go back to the last time well, let's go back to where we derived it. Maybe here. So this was the formula that Bohr derived for the energy of the different quantum states within hydrogen. So here is the formula, here is the numerical evaluation of those quantum states. All right, very good. So we got through chapter 37. We're ready to move on to more detailed quantum mechanics.